Good morning, everyone. Today I am presenting our project Beyond ML, where machine learning evolves in the terminal. Machine learning development today is fragmented. Developers constantly switch between tabs, scripts, dashboards, and AutoML platforms. The context switching slows experimentation, productivity. Existing AutoML platforms are often heavy browser-based options or a black box solution which doesn't tell what is happening underneath the cloth. Beyond ML solves this problem by bringing the entire machine learning workflow to the terminal through a structured multi-agent orchestration system. In a typical workflow, a developer performs EDA using Jupyter Notebook, writes feature engineering code separately, writes and runs training scripts manually, uses dashboards to check metrics, and tunes hyperparameter using flow grid search. This process is disconnected and inefficient. The feedback loop is slow, and the experimentation becomes time-consuming. We wanted to create a system where everything happens natively in the terminal with full transparency and real-time insights. Beyond ML is a terminal native machine learning orchestration platform. It integrates exploratory data analysis, outlier handling, feature engineering, model training, and hyperparameter tuning. All of this happens using multi-agent orchestration system built using LangGraph. Instead of treating machine learning as a sequence of scripts, we are treating it as an orchestrated workflow. Now let me explain how the system works. When a dataset is provided, the orchestration system loads the dataset and activates the workflow. The EDA agent analyzes the dataset and generates charts. The outlier handling agent detects outliers and develops measures to handle them. The feature engineering agent transforms and prepares the data and dataset. The model training agent builds the models, and finally, the evaluator agent computes the metrics. If optimization is required, the genetic algorithm module evolves model configurations using selection, crossover, mutation, and elitism. The best performing model is selected automatically. All the results are streamed live in the terminal. Now let us take a look at the terminal interface. Beyond ML uses three-column architecture system built in terminal using textual. Textual is a framework from Python. So there are three columns we need to fill. One is the dataset file path, another is an optional dataset description, and the analysis. We can select explore dataset, supervised machine learning, and unsupervised machine learning. So the default we have given is an Iris dataset, and let us try to do supervised machine learning algorithm on it. So we'll click on start pipeline. Now the orchestration system loads the workflow and starts the EDA process. It will take a little time due to the complex and heavy machine learning algorithms it needs to work. So the dataset has been integrated into the terminal user interface. We can see that currently dataset has 150 columns and 150 rows and 5 columns. It has generated four charts. So one is a scatter plot between sepal length and sepal width. One is a histogram of petal length. One is a correlation matrix and a box plot of sepal width. And according to our model, EDA is complete. It has suggested a target column species. We can just click on enter to accept it. Then Groq has identified two outliers in sepal width. There are a few ways we can treat this outlier. We can remove them and we can cap them at their maximum values, or we can use np.log1p transformations. We'll just remove them for now. So feature engineering agent has derived five new features, which are sepal area, sepal petal length ratio, sepal petal width ratio, and petal sepal length differences. So the dataset currently has 10 columns and 148 rows. So and the GA trainer has detected we need to use random forest for optimum model. So we can go with random forest or we can choose any other machine learning model if you want. Let us go with SVM. And now the genetic algorithm module is checking the population size, number of generations, the crossover probability, mutation probability. Now the genetic algorithm module has started the mutation process. It will take a little time because the genetic algorithm has to run 50 generations of 30 modules, each with a slightly different hyperparameters. After the feature engineering and genetic algorithm has completed, we get a hyperparameter tuned model with optimum hyperparameters and the machine learning pickle model. We can just copy the hyperparameters to the new dataset, new Jupyter notebook, and do the training there, or we can directly export the pickle model to the final output model. Let us wait for the dataset completed. Till then, I'll show you the UI. At the left side, we have a pipeline which shows the current progress. The middle is the whole main data where the data being stored. And in the top left right corner, we have the dataset shape, target, task, number of classes, and number of features being added. At the bottom right, we have dataset preview where we can see a preview of dataset, sepal length, sepal width, petal width, species, sample area, petal area, sepal area, all has been generated. Now we have generated the final evaluation model. We have gotten a score of 95.77%, and these are the optimum parameters. N estimate is equals to 410, max depth is 12, minimum sample is 17, minimum sample leaf is 5, max features is 0.5. Now it has generated a confusion matrix and feature importance also. So this is it has also a built-in feature for detecting time series models and a feature to implement ensemble learning methods if the accurate percentage, if the test score is very low. So this is the current model we have developed until now. We are planning to implement more features into this and make this a complete machine learning orchestration pipeline built natively into the terminal. Any appreciations and feedbacks are appreciated. Thank you.